Are we live? Can you close that door? Huh? Can you close that door? Okay. Hey everyone, welcome to this TCS session. So today we'll be looking at uh, NLP architecture called transformers and how to use it easily in Python using the Hugging Face library. So what exactly is transformers? So back in 2018, there was this new architecture called transformers introduced by this paper. Let me. So a bunch of guys from Google introduced this new architecture called transformers, which revolutionized the entire deep learning space. So it's a very simple encoder-decoder architecture that takes in a sequence of inputs and outputs another sequence of inputs, but they did it in a very unique way using something called attention. We'll not go into the details of what it is, but we'll instead focus on how to use it in code. So this is a paper, you can check it out if you want to. But in simple terms, let's say you had your task was to translate text from English to any other language. So let's say we have simple text. Let's say hi, Adi here. Oops. Yeah. So let's say you want to translate this to some other language which has uh, different script and different words. Okay, and I'll represent that using these boxes. So in a classic transformer architecture, you have this huge neural network encoder that takes in this input. So this is 0, this is 1, this is 2. So it takes in this input and it outputs a latent vector. Now, what is a latent vector? It's just a vector of dimension n cross 1. And this is an accurate representation of this text right here in some latent space. Now, there's another decoder architecture that takes in both the latent space and and the inputs one by one and outputs the translated text. Now, this is only for translation, but transformers have been used for literally everything today, starting from image generation to image tagging to speech generation to speech recognition, whatnot. You'll find transformers everywhere today. So, this is the basic architecture that we'll be working with. Now, coming back to what we'll be doing today, I have this collab notebook ready. So let me just quickly select GPU runtime and let's see what we have here. So for the sake of today's session, we'll be working with a data set called the XNLI. Uh, let's open up XNLI's web page so we'll have a better idea. Huh. So the XNLI is a cross-lingual NLI corpus. So cross-lingual just means multiple languages. So the same sentence, the same data point in the NLI corpus has been translated to multiple languages, 14 different languages to be exact. And what is NLI? NLI is natural language inference. So a classic, okay, let me just go back to this. So if you go to the XNLI on Hugging Face datasets, Hugging Face has this library called datasets which hosts all datasets, and it's like pretty easy to use. So I'm using that here. And if you go to XNLI in the Hugging Face website, you can select from 14 different languages. So I'm going here for English so that we can understand, and we are going for the training split. Now you can see there are two sentences and a label attached to it. Now what does this mean? So there's a premise, there's a hypothesis, and there's a label. So our task or the dataset's task is to classify two sentences as either neutral or entailment or contradiction. So let's take at some yeah, let's take at gays and lesbians, and that's the premise, and hypothesis is heterosexuals. So these two sentences are not really talking about the same concept. It's talking about two different things: gays and lesbians and heterosexuals. So now that is a contradiction. Now let's take some other example that we can understand. Okay. He started slowly back to the bunkhouse, and he returned slowly to the bunkhouse. So these two sentences are talking of the same exact thing. The person slowly going back to the bunkhouse. So these two sentences are entailment. So they are referring to the same thing. And it is neutral if the two sentences are either completely not related to each other, or they are not exactly talking about the same thing, or it is not a contradiction. So basically, there are two sentences and there are three labels. So in the point of a deep learning slash MLAI perspective, you will have to take in these two sentences in input and give out either of the three labels 0, 1, 2 for entailment, neutral, and contradiction. So now let's play with the data set a little. So, okay, so we have a GPU in this runtime, so that's great. Now I'll go ahead and install the datasets library and the adaptive transformers library. Adaptive transformers is a fork of transformers with adaptive functionality, which we'll talk about later uh, in this session. Just a second. Okay, yeah, great. So the Okay, so the libraries are installed. So I'll import load dataset function from the dataset library, and I'm loading the XNLI dataset and its English split. This should take some time, but you can see that, yeah, great. It's around 466 MB. It'll take some time and it will fall somewhere in the cache folder. So let's wait for that. Yeah. Meanwhile, let's talk about we are done with XNLI, we are done with attention, and we have, huh. So the XNLI dataset has a paper which came out in like 2018. It talks about how they came up with the dataset, what they use for translating the sentences into multiple languages, and they also give a baseline method. Uh, yes, no, sorry, right here. Okay, so they use BiLSTM, which is another architecture, uh, kind of architecture that came before the transformers, and they also use crossing. Okay, this is we are not concerned with that. So what we are looking at is using this method, using the BiLSTM Max architecture, they got an accuracy of 73.7 in the English subset, and this was back in 2018, and this is that baseline. This is what they could do best. So what we are trying to do today is use the least amount of resources, which is a collab 3 GPU. Use the open source model from Hugging Face that we can find, a good open source model, and train only the English subset of the split for, let's say, 10 minutes, or not more than that, and we see if we can beat this baseline accuracy, because transformers are so good that they can learn from any kind of data, and using the adaptive transformers library, we're able to do a little modification to the transformer architecture itself, and we're able to train it only for like 10 minutes and get almost the same accuracy. Okay, interesting. little more, and we'll be able to use this data set in our lab. I don't know if something's wrong with it. Shouldn't be taking this long to load the dataset. Come on, let's go. 464, 465, 466. Okay, great. Great. Okay, I think the dataset should now be downloaded. Okay, extracting data files. Great. Great. Okay. So now that the dataset is downloaded, if you print the dataset object, looks something like this. So there's a dataset dictionary with three different splits: the train, test, and validation. The train split has premise, hypothesis, and label, as we saw in the website, and it has around let's say what 4 lakh examples, 390K examples. And the test split has the same premise, hypothesis, and label, and it has around 5,000 examples, and the validation has around 2,500 examples. So let's just have a look at what it exactly looks like. So let's say if I print the training data set, sorry, it should be data set of train. Yeah, and then we get yeah, the same exact thing. Features, premise, hypothesis, label, and number of rows are 4 lakh. So let's just print the first example and check how it looks like. Okay, great. So the first example in the training data set is a premise, a hypothesis, and the label is 1. Label 0 stands for entailment, 1 stands for neutral, and 2 stands for contradiction. So great. And you can like go through all these labels and check if they make sense or not. But usually you'll end up trusting the datasets library and doing whatever it gives you. Now, yeah, so now this text is in English, and I'm the model that we're about to train does not understand this kind of script. So all of this will have to be tokenized to something, let's say, to numbers basically, so something that a model would be able to understand. So for that, we'll be using the tokenizer. So from the same transformers library that we installed, we'll import order tokenizer, and TQDM is just for beautiful the progress bars. So we write this tokenization function that takes in an example. Here, example is nothing but one data from this data set, one data point from this data set. So you return the tokenized text, that was, you tokenize the example hypothesis, the example premise, you truncate it, you pad it to max length, and the max length is 120. Now that's a lot of extra stuff in here. But truncation basically means, so the transformer that we are working with, this XLM Robota base, has a maximum length of 512 or 728. Yeah, it basically has a maximum length of some n value. Now, what does that mean? So it cannot take in text which is greater than n value or less than n value. So every text that you give to the transformer has to be of this length. Let's say 728. Now, what if it's more than 728? You truncate it. So you cut off all the tokens that are greater than 728. Now, what if it's less than 728? You pad it to the max length. Now, what does that mean? You take the you take the text. So let's say the tokens are only 120. You pad it to the rest of the length until it's 728 and give that to the transformer. And here I've like done some exploration with the data set and figured out that the maximum length that we need is only 120. So after that, we take a tokenizer. A tokenizer is auto tokenizer. This library from pre-trained. We'll be using a model called XLM Robota Base, which is a cross-lingual, state-of-the-art model for uh, literally any cross-lingual task. And we'll be returning input IDs, attention mask, and label. So this I'll show by actually doing it in code. Just wait a minute. And let's say data, and we'll map this function onto every example from the data set. So I do dataset.map, you do the tokenization function, you batch it, and then you yeah, this is just to make sure that you are not returning any files from the past. And you set formatted to PyTorch, and columns to returns are from this column. So we only need input IDs, attention mask, and label, and we don't need any other columns. So let's run that quickly. This should take, I don't know, around, okay, that's fast. Okay. Now to show how tokenizer actually works, I have a simple example here. So you can see that this is similar to this format. So tokenizer, we have some example hypothesis, and we have some example premise, and we don't have any of this, the rest of this, the stuff that's here. So let's just run this and see what it gives us output. Great. This should take about 10 more seconds, and then we should be fine. Okay, great. So tokenization is done. So now, yeah, as I said, we put an example hypothesis and an example premise into the tokenizer, and this is what you get. You get input IDs, you get attention mask, and then you also have labels from the data itself. So as you can see, this these two texts, which is in English right here, has been converted to just tokens, just numbers, which the model can understand. And this is exactly what we want for our purpose. So this is, yeah, here you're tokenizing it and converting it to tokens, but there's also a function for tokenizer called tokenize, which will convert this into tokens that are in English. Now, every one of these tokens have been mapped to one certain number. So it's basically a vocabulary that has this as this zero has the key, and this, sorry, zero is the starting variable. Yeah, this 89536 as the key, and the token corresponding to that in English is underscore exam. So the tokenization is a whole new topic, and we'll have to spend a lot of time on it to understand. But for the sake of this session, you just have to know that if you have a sentence in English and if you pass it to the tokenizer, it gives tokens which can be easily understood by the model. Now we can, yeah, so what if we take this exact sequence and we put it through, wait just a second. Yeah, what if we take this exact sequence and we put it back to tokenizer.decoder? You should be able to get back the example hypothesis and premise. So let's just check if that works. Sorry. Yeah, so if you encode it and then you decode it, you should be able to get back the same sentence. So this is how you take a sentence, you encode it, feed it to the model, model gives an output, you decode it, you have to get back the same sentence. So we are done with data preparation and tokenization. Now let's just actually run the model. So here I am importing some functions from the transformers library and importing torch. Torch is the PyTorch library, and I'm yeah, this is not required. So yeah, I'm downloading the model, which is a XLM Robota base, and this is an auto adapter model. So what's different in adapters? So instead of the XLM roboter base is a pre-trained model which has been trained on a huge amount of data for a huge number of days with like lots of compute and lots of resources. So we can have a look at how it was trained. XLM roboter base. Yeah, for the sake of okay, let's just okay. I'll just run the training loop and I'll explain it later because the training is gonna take around 10 minutes. Yeah, so let's get back to here. I hope this runs. Yes, it's running. Okay, so XLM roboter base on Hugging Face. Yeah, it was pre-trained on 2.5 terabytes of data from over 100 languages, and basically it's a huge model, and I think it has over a billion parameters or something. So now if we try to train the entire model on this small data set, which is the XNLI data set, the model is obviously going to overfit on the data and is just going to memorize the data. But what we want here is the model to understand how the classification happens and be able to reproduce it for new data. So what we're going to do here is add an adapter. So what are adapters? Instead of, okay, let me just explain it this way. So let's say this is your XLM robota model, okay? And this huge, it's a very huge model trained on lots of data for a huge number of days on lots of resources. But you don't want to train the entire thing on a very small data set. Our data set is hardly 3 4 MB in size. So we don't want to overfit a model that was trained on 2.5 TB of data with just 2 MB of text. So what we do is we add new layers called adapters. So this is the model, and it is made up of multiple layers that are learned through a process which is called pre-training. Now we just add new layers called adapters in between the transformer and train only these layers. So you freeze the rest of the model and you train only these few layers. And these layers are so small in size that it can be trained, the entire model, which has like 2 billion parameters, can be trained in around 10 minutes. Let's get to the training part later, but yeah, so that is what we're doing here. So we are adding an adapter called XNLI, which is nothing but adding multiple sub layers in between the existing transformer layers. And we are adding a classification head, which takes the model outputs and gives out 3 labels. And we are checking if the device, is there a CUDA device, or we'll have to train on CPU, and we are putting that to putting the model to the whatever device we have chosen in this line. Uh, yeah, to show the difference in parameters that we're training. So yeah, train our example. This is done to make sure the adapter trains. So here I've written simple code that takes the ratio of trainable parameters is to frozen parameters. So in this case, these are trainable parameters and these are frozen parameters. So you check the ratio of how many parameters you have to train uh, is to how many parameters are there in total. So I'm just for every p in model dot parameters of, I'm checking if p dot required grad is true, and p dot required grad is something that defines if the parameter is getting trained in the future or no. Now I do that for both trainable and frozen, and I do trainable by frozen press trainable into 100. You can see that we are only training 0.5% of the entire model. We are not training the model itself. We are not training 99.5% of the model. So this means that we can train it in a very fast way, and we will not overfit on the data that we are training. Now I go ahead and import some other functions that are required for training. I'm also importing the FN score, which will be a deciding metric if a model is training or not. So so training arguments. I define training arguments. These are all the default training arguments for any Hugging Face training method. So you want to eval, your learning rate is 0.0001, and you want to train it only for one epochs, and your batch size is 16, your eval batch size is 16, your training and your eval batch size is 16, and your evaluation strategy is steps. That means every 200 steps, you want to evaluate the model on the validation data set and print out the outputs. And you save your model after every epoch, and you define an output directory, which is the training output. You should be able to see that here. Yes. And these are all pretty much not required. Yeah, compute metrics is a interesting function that will take eval prediction object, and it will check the F1 score and the accuracy and return it back to the trainer object. And then we define a trainer adaptive trainer module, which takes in the model, which takes in the training arguments. It takes in the train data, and we shuffle it. We don't need the entire data set to train. We only need 50,000, around 50,000 examples. So we shuffle it with a seed, and we select 5,000, 50,000 data points. And for evaluation data set, we shuffle it, seed, select only 1,000 data points, and we send the compute metrics function in the compute metrics. And then we have defined all the stuff that we actually have to train, and we just run trainer.train off. Now, as you can see, the model has been training for around 5.48, 5 minutes, and the accuracy is steadily increasing. So it was 34% accuracy in the first 200 steps, then it went to 33, 59, 62, 68, and 69. Now, remember the accuracy of the baseline accuracy of the original paper, it was around 73. So let's see if we can beat that accuracy only by training it for around 10 minutes on Collab's free GPU. It's around 70. You can also see that the loss has been slowly decreasing to 0.7, which is great. And training loss has also been decreasing. If we increase the batch size to, let's say, currently it's 16, if we increase it to 32 or maybe 64, training would be a little faster, but I think this should do. 10 minutes is still very less time, and we should be able to work with it. Great. Okay, we have 6 more minutes of training. Uh, yeah, so we'll be able to achieve an accuracy that's almost similar to that of the baseline provided in the original paper. Uh, so yeah, if you want to train a new data set on, let's say, there are multiple data sets you can find on the datasets library. Let's just go to XNLI huggingface, and okay, let's just go to datasets. Yeah, you'll find multiple datasets on this page. There are around, yeah, there are like 12,797 datasets in multiple languages, whether they're multilingual or not, what tasks they are for, and fine grained tasks. Okay, and what are the sizes? Do you want a huge data set? Do you want a small data set? What license does it have? MIT, or is it a non-corporate license? So you'll have multiple data sets in here. You can go through. If you want to work with any one of them, you can. Amazon product. Let's just check this one. Yeah, you can just take this data set, understand the data set, clean the data a little, figure out which transformer will probably be suited for your data set task, and train the model on that data set and see how well it does. So all of this has become much simpler with the data sets and transformers library, and you can do it uh, fairly easily with like around 200, 300 lines of code. I think yeah, this should be pretty good. If you let the model train for another 4 minutes, it would reach an accuracy of, let's say, around 79, 80, which is good enough for us, which is much better than the uh, accuracy given in the original paper. And yeah, mind you, this they trained a BiLSTM max model. Let's figure out, let's see if we can find what was the number of parameters and the model. Do they have? Okay. Uh, Great. Mhm. Yeah, they haven't mentioned the size of the model, but okay, yeah, the classifier is a preferred neural network with 128 neurons. Okay. Uh, yeah, so basically it's a bi-LSTM model that uh, uh, was trained for probably much longer than 1 hour on this huge data set to get the desired output, but we should be able to do the same by training only for like 10 minutes on 0.5% of the original parameters. Let's see if we can get one more result. Should be hitting. Okay, sorry about. Okay, I think we can say my changes. We can stop here and see how well it does. Okay, let's just. Yeah, I've written this simple code that defines metrics for the English language, and you do trainer.predict of data of test. You add the FN score, you add the accuracy, and you add the loss function. The loss. This should take around yeah 19 more seconds. Let's make let's put that into a data frame so that it's you can decide easily. Great. So we have an accuracy of 72%, F1 score of 72, and loss of 67, which is pretty close to the original baseline. And I'm pretty sure if you train it for like 4 more minutes, it will cross the baseline. State of the art performance for English for the same data set is around 89 90%. So if you can make some minor changes to this model and like clean the data a little bit, add some more adapter layers, uh, do some minor modification, change the with the trainer, change the maybe change the batch size a little bit, train it for more epochs, and change the learning rate gradually over time. We should be able to easily beat the state of the art with just 300 lines of code and 10 to 20 minutes of training. Uh, you can pretty much take any data set from the datasets library, pick a transformer of your choice, and then train it on the dataset and get state of the art result right in your collab without having to worry about a lot of compute or resources. But it does get inefficient when you have a lot of data to work with. Adapters kind of underfit on huge data, and if huge data and your accuracy might not be as good as state-of-the-art models that use the entire 2 billion or 3 billion parameters to learn a single data set. So yeah, for most cases, adapters are great for the transform architecture. Some cases they don't perform so well. So it depends on the task and the data you're working with. Uh, so yeah, we got around 72% accuracy, and I think uh, that's all for the session. We can end it right now. If you have any questions regarding the transform architecture and how to, let's say, train a new data with a transformer, you can approach me and we can discuss about it. Thank you.